make a box with a square base. And so here's my base, and it's going to be, or maybe I won't have that in my base. Here's my box. My base is going to be down here. It's square. So if it's square, I know it's going to be x by x. And my height. And I want the largest possible volume of my box. Well, if I'm going to have a large volume, well, volume I know of a box is going to be x times x, which is the base, times the height. And so I have too many variables now. I have to take my variables and get rid of one of them. The one variable that one thing I know is that I got 2,700 centimeters squared is my surface area. Well, if I think about my box, it's an open top. If I open it up, here's my square base, x by x. If I pull down the sides, I'm going to have one side here, and here, and here. And these are my heights, h all around. And so I have these four rectangles are all the same. And that area is, there's four of them, well, x times h. So one of those rectangles is x times h, and there's four of them. Plus, the bottom is x squared. That's my surface area, and that is 2,700 in total. And so I have an equation with two variables. I can substitute it in. If I solve for h here, I'll subtract x from both sides of the equation. So if I have 4 is equal to subtract the x squared, and then divide by 4x both sides. And I know that h is 2,700, 2,700 minus x squared over 4x. I'm going to take this equation, plug it in to there. That's the key. Okay, oh, I lost part of it. 4x. So now volume then is going to be x squared from here. H is simply 2,700 minus x squared over 4x. Now, this is the key step. Making this equation is the hard part, I think, of these equations. And once you do enough of these optimization problems, you start to recognize that there's a quantity that you wish to optimize that usually has two variables in it, and another piece of information somewhere you're going to have to substitute an equation in. That's a kind of a general kind of thing for these problems. Now, solving this, I can cancel this x with one of those x's. And so then volume, distribute the x in, I get 2,700 over 4x minus x cubed. 2,700 divided 4 is 675. So I get 675x minus x cubed. Now, over 4, yes. Can't forget that part there because this is a 4 down here. Okay, always good to make sure you double check your work. So if we go along here now, I'm going to take a maximum, means I'm going to take the derivative. So the derivative of volume with respect to x is going to be 675 minus, bring the 3 down, times the 1/4. I'm going to set it equal to 0 because I want a maximum. And if I do that, I end up with 675 is equal to 3/4 x squared. I'm going to multiply both sides by 3/4, or 4/3 rather. And so I know I get 2,700 over 3 equals x squared. And this is 900 x squared. And so x equals, take the square root. I get plus or minus 30. X is a length. So I can ignore the negative part. So I get x equal to 30. If we look at our question, it's talking about specifically find the largest possible volume. Well, let's go and make sure we have a maximum. So we take the derivative over x, make a sign chart. This is volume. I know this is 30. I plug a value into my derivative that's less than 30. I get a positive, which means increasing. If I plug a value that's bigger than 30, I end up with a negative, which is going to be decreasing, therefore a maximum. To find the actual volume, I know that I have the equation. Where'd it go? 675 times 30 minus 1/4 30 cubed. If I do my equations on that, I get 675 times 30 minus 0.25 times 30 to the power of 3, which is 1350 centimeters